Hello guys, and welcome to the next tutorial of ethical hacking and penetration testing via Kali Linux. So in the previous tutorials we had a look at DHCP spoofing, poisoning, DNS poisoning and ARP poisoning. But there is one more term before you could get rid of the MITM attacks, and that is ICMP redirection. And this is quite different from all the other attacks, the reason being that, okay, I'll tell you later on that. And by the end of this tutorial, you will be having sufficient knowledge for going ahead and doing all the MITM attacks out there and how to prevent yourself from them as well, unless you don't fall prey to social engineering. And yes, and the last thing that I would be teaching you by the end of this tutorial would be how you could go ahead, and I would actually practically like to show you a few examples of how we could go ahead and use Ethernet or EtherCap to go ahead and actually capture some packets and get data out of them by stripping off SSL security or sniffing and spoofing and going ahead and gathering information over the MITM network and becoming a man in the middle. And yeah, that's right. So first let's start with the ICMP redirection. So an ICMP redirection is an error message sent by a router to the sender of the IP packets. So redirects are used when a router believes a packet is being routed, you can say as suboptimally, and it would like to inform the sending host that it should forward subsequent packets to the same destination through a different gateway, because that gateway is not able to perform in a good or sufficient data analysis, due to which it is not able to send the proper packets in the same direction. That's why it will ask you to go ahead and send it through a different gateway. So in theory, a host with multiple gateways could have one default route and learn more about optimal specific routes over time by the way of ICMP redirect. So let's consider the following diagram. This diagram, simple. So in this figure, you can see that host A over here, it wishes to send a packet to the host B. The routing table on the host A consists of a default route through router R1, that is, which is one over here. And when R1 receives a packet destined for host B, it looks at its routing table and notices that it has a route not default to R2, that's router 2 for packets, but that is destined for host B. So therefore, it forwards the datagram to R2, which in turn passes it along to the host B. Router 1 also notices that the outgoing interface and network for the packets was the same as the interface it arrived on. Since it is configured to send ICMP redirect, it sends an error message to the host A informing it that all packets destined for host B should be forwarded to R2 and not to R1, or else it will not be able to go ahead and communicate with the actual Ethernet part. So it makes sense for router 1 to send a redirect because host A could have just as easily sent packets through R2 to start with. Sending packets through R2 directly would decrease the number of routing hops for host A and increase the performance on R1's link. Obviously, redirects would not be involved if host A contained a static route to R2 for packets to host B, or if R1 could forward packets to host B through a better path such as directly connected interface. So if this was directly connected, or if it would somehow go ahead and pass all the data to router 2, then it would be sufficient. But since it cannot, it will straight away go ahead and give an error message to A that it is not able to go ahead and send the packets to actual connection B, because for the router A, it does not even belong over there. Means it will not even recognize whether there is a host B. It will only think that there is host A, the reason being that it is only connected to A, that's why. So it will go ahead and send an error message, but the computer host A will not stop looking for the correct path. It will go ahead and try to send it to the router 2, that's R2 over here, and then it will be able to connect to B. So there are different ways of connecting. However, there are different rules for the route, and there are several governing that govern the rules of ICMP redirects and their acceptance into a host routing table. Before an ICMP redirect is generated, there are following restrictions that are typically adhered to on most of the today's routers. The first thing is that the outgoing and the incoming interface of the packet must be the same. If they are not the same, that means somehow they were disauthenticated in between, and either part A or either the host A or host B will not accept it back again, and it will just go ahead and dissolve in the whole network when the data network transfer starts again. The IP source address in the packet, that is the second one. The IP source packet the IP source address in the packet is on the same logical IP network as the next hop IP address is. To be more specific, if it tries to go, if there is no connection between them and the IP address source is different, because for example, let's say it's 192.168.1.1 and over here it's 192, or you can say it's 172.1.1.1, something like that, anything random, but it is different from the source of over here A, then it will again not be able to collect. The reason being that there won't be any connection within the LAN network if both the IP addresses have a total different configuration. The third thing is that the route used for the outgoing packet must not be an ICMP redirect or a default route. To clarify it a bit more, let's say A has transferred let's say 8 MB packet to 8 KB packet to router A. So this is the default way, or the gateway for the host A. This is the default router, that is the gateway. So but at the same point, this is also the ICMP redirect path for host A, because when it transferred to go ahead and when it tried to go ahead and transfer some data to host B, it redirected it back to A, stating that there was no such connection as B. So to make sure that you have a connection with host B, there should not be one should not be either the default, or one should not be either the redirect gateway, because if both are the same, then it again won't be able to connect. But if one is the default gateway and it is ICMP redirect, then this should be the default route, else it won't be able to connect. Or if this is the ICMP redirect, then this should be the default gateway, else it won't be able to reconnect. The fourth part would be the packet data does not contain an IP source route option. So that means that if this has any random IP address, then the packet that is being sent should not have a gateway or let's say an IP address configured by a different gateway. The reason being that if they are on the same LAN and they have different gateways and different IP addresses, again they won't be able to reconnect. They should have either the same gateway or a same type of IP addresses in the same similar manner, or else it won't be able to reconnect. And the fifth and the foremost important part would be the gateway must be configured to send redirects, so that if router 1 is not configured to go ahead and send any redirects, then it will keep on trying to go ahead and connect to B. It will not even redirect any traffic back to A, so it will still keep thinking, or it will still keep looping the same thing again and again, and it won't even be able to sense that it was not able to connect to B, because the router 1 will never tell A that there is no connection B. It will just go ahead and consume all the data bandwidth in between. It will get destroyed, and it will just be like a black hole. You're just trying to send something, but you're not receiving anything back, and you won't even know what is happening over there. That's how it works. But if this is configured to go ahead and redirect it back to A or to router 2, then it will straight away go ahead and redirect to either of those, and then it will be able to send the packets. So RFC 112 of 2, that is the, you can say a section something like that, it states that the host should not send ICMP redirect. If A is able to redirect an ICMP, let's say for example, if A has sent some packets to 1, it should not be able to redirect the same packet to the router 2, else it will not be able to send, the router 2 will not be able to send it to host B, because router 1 has already went ahead and denied that. That's the reason. So whenever it receives a redirect from the router 1, the A should go ahead and particularly deny or destroy the data and resend a new packet with the same data to the router 2. Else again it won't be able to reconnect after that. So there are specific kind of particular routing table that one needs to know properly before they go ahead and actually connect to the ICMP redirection. And multiple other, you can say, as checks that are typically performed at the host, and they're not all mentioned in the RFC 112. And just if you're wondering what RFC 112 is, I'll just go ahead and show that to you before I close this tutorial. So I can just type, I'll just go ahead and connect to my website. Yeah, perfect. Okay, after surpassing my gateway, I'll just go to RFC 112. As you can see, RFC 1122, that's requirement for internet host communication layers. They have set up different types of walkthrough through which we have to go ahead and configure each and every protocol. If they don't you can say as don't satisfy that, then they won't be able to reconnect, or they won't even be able to go ahead and actually surpass anything along. So that's it for this tutorial, and in the next tutorial I'll be teaching you the different ways of connecting and what are the different checks that must be performed, but they're not listed in RFC 1122 before adding a redirect route to the routing table. So that's it for this tutorial, guys. Hey guys, welcome to the next tutorial of ethical hacking and penetration testing via Kali Linux. So in the previous tutorial we saw a look at ICMP redirection, and RFC 1122 states that the host should not send ICMP redirects, and however, just as the default gateways follow a set of guidelines as to whether they will send redirects or host also have a built-in specific set of guidelines of protections to prevent inadvertent additions to the routing. So I'll now teach you about the following checks that are typically performed at the host, not all of them which are listed at RFC 1122 before adding a redirect route to the routing table. So the first one would be the new router must be reachable through a directly connected network. So if this router is connected through some other router, that's some other computer, and it finally goes and reaches back to A, it won't work because it should be connected directly to the computer A, else it will not. The new router must be from the existing router for the destination in a question. So to simplify it, let's assume that router A is our main router, and this is a remote computer and this is our original computer. If I send a packet to that remote computer, and that sends a packet to the router will not be able to redirect it back to A. The reason being that this specific computer, that is let's say a remote computer, it only accepts connections and data from A, whereas it only sends out packets to this specific router. It will not go ahead and accept anything back to A. So in order for the router to go ahead and connect back to A, it should be connected directly, not remotely. The third point would be the new route cannot specify the host as the next hop address. So let's consider something as, let's say for example, A has directed a packet to the router 1, and 1 cannot go ahead and redirect the packet to B through A or through the router. Means no, it can do through the router, but it cannot go ahead and send it to the same host to connect it back to B, because B will not be able to then recognize whether it was sent by A or 1, and it will be again in the loop as to from where it was sent in total. So that it should be connected either such as A, 1, 2 and B, or A, 1, A, end, and a new packet should be sent to the router 2. And yeah, that's how it will work. And the fourth point would be the redirect route must not point to an address on the local subnet. And the last point would be the host must be configured to accept redirects, because if A is not configured to accept redirects, and if the one goes ahead and passes the redirect, A will think of something like something is trying to pass the data along through A, and again it will go ahead and redirect it back to B, and again the loop will start and nothing will happen again. So in practice, some operating systems perform more security checks than others when adding redirect routes. So Windows is good in redirecting, but I would not say that it is very awesome or something like that. Even Ubuntu is good at that, but the best feature which I would like to tell you would be from the Fedora and the Red Hat, because they are very much awesome in going ahead and configuring redirects, because they are made for that specific purpose, for being used by system administrator to know where each hop is connected, where each host is there, and where each route is there, which router is going ahead and redirecting all the parts, and they need to make sure that one is not redirecting the part back to some third party over here, which is a malicious attacker again. So now let's talk about the raw data. So the ICMP redirect error message is consistent with the format of all other ICMP error messages. So this is a breakdown of what the ICMP redirect packets look like. This will not give you much of an idea as to how exactly it should be, but this is how it would look like. The redirect message contains an ICMP type of 5 and a code between 0 and 3, that is from over here, 0 and from 3, that is where the code lies in between. The next comes the checksum and the IP address of the next hop router that should be used. Finally, the IP header and the first 8 bytes of the offending packets are included as a part of the ICMP data, and by offending packets I mean the packets that were redirected back to A and not the original packet, because once the packet is sent back to A, so I'll just go ahead and show it out to you. So once the packet is sent out from A, that is not the offending packets, but when it is sent out from one back to A, they are the offending packets. And this code field will allow the following types of redirect messages to be sent. So this is how it looks like. Notice that there's no place in the packet to delineate or a network mask. In practice, only codes 1 and 3 are usable. I'll just go back to the previous one. Only codes 1 and 3 are usable because a host cannot accurately guess the network mask in which the destination fails. Network redirects were designed in the days of classful routing when masks were implied, but very few networks are still deployed this way today. Based on the information purpose so far presented, it would seem that ICMP redirects serve a quite a useful purpose. In fact, they do. Yet there are several reasons to steer clear from redirects, all of them relating to network performance, consistency, reliability, and security. And as you can see, 0 is the redirect datagram from the network, redirect datagrams from the host, that is 1, 0, 1, 2, and 3. The second one is the redirect datagram for type of service and network, and the third one is the redirect datagrams for the type of service and the host. So networks that qualify for ICMP redirects are inefficient. This inefficiency stems for several reasons. Firstly, packets that enter and exit the same interface and IP network towards their final destination are taking a suboptimal routing path. These packets should be forwarded through a different gateway in order to reduce the number of routing hops and in turn decrease latency and increase network throughput. Packets that enter and exit the same interface of the router are they are effectively doubling the load on that link. Secondly, as we noted earlier, ICMP redirects are not only host based because it is not possible for a host to guess for which networks a packet is being suboptimally routed to. So just consider this following program over here. Once again, host A would like to send a packet to B. The routing table on host A consists of only one default gateway and no other static rules. And this is the routing table from output from host A, that is a FreeBSD 4.6 system. And if you don't know what FreeBSD is, I'll just go ahead and show it out to you. It is mostly used for creating a firewall, and it has its own brother known as OpenBSD. I'll just go ahead and show it out to you, the operating system. As you can see, here are the latest releases. You can just go ahead and click on that link and download all the parts that you need. And FreeBSD is an advanced computer operating system used to power modern servers, desktop, and embedded platforms. And this is quite a good and secure operating system, I can say that. And yes, you are right, you heard it right, it's an operating system, and it is not like the Linux or Unix that you would use. I'll just go ahead and show out an image to you as to how it looks like. Yeah, this is how it looks like, and yes, this is how it looks like in actuality. Just ignore this part. So this is how it looks like in actuality. You have Wine over here that can go ahead and run Wine programs. You have the pig, the snort, the buffalo that can go ahead and run multiple programs out there, even the Mac programs. And finally, you have Mozilla to safely go ahead and browse or go through whichever things that you need. And it's mostly used to go ahead and create, you can say as, let's say, for example, to go ahead and secure or create a firewall so that everything that comes in and goes out will be seen by FreeBSD, and it will keep logs for you to go ahead and understand how exactly or who exactly went through the records and how it will work exactly. Go ahead and start. Okay, so coming back to our tutorial, I'll just go ahead and show you one more thing. To see if host B is alive, host A sends two ICMP echo requests to host B as follows. And notice that host, as you can see over here, when you go ahead and ping it, notice that host A did receive an echo reply from host B. As you can see over here, packets were being sent out and it redirected host and was sent out back to A as well. So, but it also received, notice that A did receive an echo reply from host B, but it also received something it may not have bargained for, that is, one ICMP redirect for every packet destined to host B. This would have continued indefinitely until host A cancelled its ping, as we have done above. As you can see, I have gone ahead and cancelled the request, else it will still continue, and this arrow C, upper arrow C, means that I have gone ahead and cancelled that. So Even though host A received an ICMP redirect for every packet, you may think that why did not it take a new path right away? If we examine the routing table on host A once again, you notice that a host-based route was indeed installed for the IP address 10.0.1.32. I'll just go ahead and go back to my previous. So this one, it was already configured to go ahead and route it back to A, but it did not go ahead and actually redirect anything. So it would appear as if the ping program does not re-evaluate the routing table during runtime. The reason for this is explained quite elegantly by a guy named as Richard Stevens, who points out that this happens because there is no control input function for the raw IP protocol. It's only there for UDP and TCP. Since ICMP lies just above the IP layer, the redirects appear to be ignored. Thus, changes in the routing table are not taken into account until we stop and rerun the program like I have done so over here. Okay, so that's how it looks like in reality, and we need to go ahead and cancel that one again, but I won't be explaining this to you in this tutorial. In the next tutorial, I'll be continuing the same part, so make sure that you have watched this tutorial first and only then you go on to the next tutorial, guys. Hey guys, welcome to the next tutorial of ethical hacking and pen testing with our own operating system, Kali Linux. So in the previous tutorial, I taught you about the ICMP redirection, and just before I proceed, I'd like to give you I'll go through a short discussion of my previous Okay, so over here it would appear as if the ping program does not reevaluate the routing table during runtime. The reason for this is explained quite elegantly by Richard Stevens, as I told you previously, that this function only works for raw IP protocol, that is UDP and TCP. So this time our packets have taken their expected path and travel immediately through R2 rather than first traversing the default gateway R1. For every destination that host A receives a redirect, it will install a redirect host based route in its routing table. In this small example, it could potentially install up or set up to 255 routes and 32-bit mask. Just consider how many potential host-based routes this could generate for networks with more inclusive prefixes. For example, a single route with class B mask potentially add up to 65,535 redirects. Certainly, it would be better for host A to be fitted with some better method of discovering what traffic to send through R2 instead of relying on ICMP redirects, because actually going ahead and redirecting 65,535 redirects, it sounds exhausting, and it is exhausting, because if you go ahead and try to do that, you may not even be able to get the redirect, stating that you will just be in a loop and you'll be waiting like forever to go ahead and get the redirect. Thus, depending upon the OS implementation, these host-based routes can have the characteristic of being short-lived. Solaris implements aggressive aging, where Solaris operating system it implements aggressive aging where redirects will only last for a specified amount of time. So let's say, for example, if I have redirected something to A and it does not respond for, let's say, around 10 seconds, 20 or 30, whatever the time may be, then the timer will expire and it will not be able to go ahead and send anything back. Each redirect is given a short lifetime value and will be automatically removed from the routing table when the timer expires. This is to ensure that redirects do not remain in the routing table indefinitely, at the risk of further going ahead and freezing other data as well. So in BSD networking code, redirects will be removed if they are being used by TCP, and only after the fourth consecutive retransmission attempt they will be removed. Router and gated perform similar forms of redirect expiration. Since ICMP redirects are dynamic and may not reflect the most current topology, it is nice to have an automated method of redirect expiration. Note that ICMP redirects can also cause problems in firewall environments where flow traffic patterns are non-deterministic. Just consider this following example. Figure 3 looks like, okay, just let me check. So over here, this figure looks quite similar to the previous diagrams, but suppose that host A's default gateway is not a firewall, that is, it is now a firewall instead of a router. If host A were to receive an ICMP redirect from its default gateway, probably only part of the traffic flow from host A to host B would be seen by the firewall. Asynchronous flows pose particular problems for stateful firewalls because they need to see the entire flow cycle. This is especially the case for TCP traffic when individual packets can point to state transmission such as a beginning, such as SYN or sin-ack, or the middle such as the ACK-PSH, or the end such as fin-ACK-RST. If the firewall were only to see the beginning of the flow or part of it, it may take an extra long time to time out entries from the session table because it was not able to see the middle and the end of each flow, and again it may again go over and get disconnected. So the problem is accelerated if an ICMP redirect only gets acknowledged by a host after the initial TCP handshake has completed. Firewalls rely on timeouts to age out old entries in cases where TCP control traffic is not available. Although embryonic TCP connection timeouts are generally an order of magnitude smaller than timeouts for established TCP connections, they can still lead to firewall session entry table converting into exhaustion. So a common design flow is that firewall security in this topology could be bypassed altogether if host A were to simply create a static route to host B instead of using its default gateway. This is probably not what the network architect intended when placing a firewall in front of the host A if she or he was looking to filter traffic properly from host A to host B. So in short, what I'm trying to say is that whenever some data has been sent out, the host A should know whether it should use the default gateway through a firewall or a blocked router, or it should know that it should go through the port 2, that is router 2, through which it should be able to connect to B. So the person needs to know, the data needs to know where it is actually going through. Finally, redirects could be used by an attacker that has some knowledge of the network topology to inject malicious routes into the host routing table. This could case a denial of service against the host or specific destination it is trying to reach. One example of such a program would be ICGen. I'll go ahead and talk about that at the later part of this tutorial. It is a utility developed by an author simply for research that is capable of sending any type of ICMP unreachable message. Older Microsoft variants are much more susceptible to this form of attack since less security precautions are out in place, and newer operating systems make this more difficult to spoof, but not altogether impossible though. But there is still a good news. Fortunately, there are effective tactics when dealing with networks that wish to send ICMP redirect, aside from disabling them altogether, because disabling them will not just go and help us, right? That's why. So generally these types of network can be re-architected through one of the following means. A. Changing the network configuration to remove the possibility of multiple non-redundant gateways for a host. B. Changing the network configuration to make the gateways redundant. C. Adding optimum static routes to the host for the networks in question. And the last and the foremost important, adding the capability for learning dynamic routes to a host. So, and the last and the foremost part would be, not the foremost, the ultimate thing that you would like to do in your environment would be to go ahead and make the host intelligent enough to understand whether it should go ahead and pass through a firewall or it should go through any other gateway through which it could go in and get access or give access to host B. And the firewall should be good enough to understand whether it should go ahead and force feed the data to go ahead and cancel itself if it's going to go through another gateway, or it should go ahead and allow it quickly just by going ahead and scanning it from the start to middle as well as the end, and knowing how to go ahead and redirect that. So though ICMP redirects serve to point out issues with suboptimal routing, network re-architecturing should be favored over their use. Well-designed networks should never lend themselves to the reliance on or desire for ICMP redirects for reasons of performance, consistency, reliability, and security. ICMP redirects are bad, that's why. So in short, that you should make your network so good that you should be able to know whether it should be able to or in fact you should not go ahead and disable ICMP redirection, I'm saying. But what I am trying to convey is that you should be able to know whether you should be able to go ahead and transfer data through different routes and through different gateways, and even if let's say for example, if the host A transfers some packets to, let's say let's assume that this firewall is a router. I'll just go ahead and go back to my previous one. So let's say for example, if the host A tries to send something to host to the router A, and as soon as it gets the redirect, it should go ahead and quickly pass it through router B rather than going ahead and searching default gateways. So there should be specific gateways set up already before anything goes further on, so that you know exactly what is happening and it should know exactly from where it is going. And the final thing that I would like to convey to you would be avoid traffic jams, try quantum tunneling. It is the most famous quote of all time. I don't know who said it exactly, but this is very famous. So quantum tunneling, to be in technical terms, I can say as using a secure layer. It is going ahead and using there's a most famous application which is used, that is called as Putty, P-U-T-T-Y, and you can go ahead and download it from over here. Let me just show it out to you. So as you can see, this is a free SSH and Telnet client for Windows. And Ubuntu, Kali Linux, they have all inbuilt SSH clients, so you don't need to worry about that. For Windows, you can go ahead and use this, and this is a very, or I can say extremely secure Telnet client used by most of the people out there. You can go ahead and connect to any Windows you want through the SSH tunnel, and you won't even face any kind of traffic jams because it's quite or extremely fast, and you can run multiple computers, whereas using graphic user interface can go ahead and run only one computer. Yes, so that is it for this tutorial, guys. In the next tutorial, I will actually be going ahead and showing you some actual examples of going ahead and killing your network, or using some tactics to go ahead and defend your own network, as well as using your exploits and injecting them into softwares. And at that point of time, we will be using ItterCap, which is again used for man-in-the-middle attacks.